The discussion in this episode, network authentication, coming up next.
Never
Oh,
good
don't
when
worry
he
about
goes,
it. That's okay.
I don't know why that happened. I was really
ponder.
expecting something totally different.
It's almost like what I expected, only
You're
not.
watching MyITproTV. You're watching MyITproTV.
Alrighty then. I'll go take some Dramamine real quick. Hold on, I'll be right back. You all right there, bud? Okay. It's okay. You don't have to apologize, man. Yeah, no worries, man. Like I said, it's a learning process. We're all learning. And Senior Taylor, are you ready, bud?
Yes, sir.
Okay. Coming up, a conversation in network authentication. Stay tuned.
You're watching MyITproTV.
Hello, ladies and gentlemen. We're continuing our discussion through implementing advanced network design, and discussing network authentication is Adam Gordon. Adam, how are we doing, sir?
Doing well, doing well. Hopefully all of you are also. We're glad you're joining us yet again for another enticing and engaging episode around implementing advanced network design. We're in subtopic C in topic 8 of our CASP discussions. We just wrapped up a conversation around remote access, but really more importantly, spent the majority of the episode focusing on IPv6 and specifically transition technologies that let us coexist in a dual stack environment. Remember Teredo, 6 to 4, and ISOTAP in no particular order. Definitely want to go back, check that out if you haven't seen it. It'll be important for you to distinguish between what those specific bridging technologies do, how they work, how they're very similar, but also the specific business cases that may be used or necessary for them to address in order to be used. For instance, remember when we talked about Teredo, that was specific to NAT traversal and being able to move IPv6 traffic through a natting solution versus 6 to 4 that simply let us send IPv6 traffic over an internet without worrying about whether it was being natted because we weren't going through a natting solution. So important to understand the scenarios you may see there as you engage with that content. I'm going to move on and continue our conversations in advanced network design. Network authentication is another area that I find many clients, many customers, many students don't really spend as much time thinking through as they should as they begin to not only roll out solutions, but also then have to worry about supporting them over the life cycle of that solution and securing access and requiring perhaps moving from single to dual or even multi-factor authentication scenarios over time, and what those impacts, those choices, those considerations may be. In other words, to be blunt, what I often find is that we rush to deploy a solution without thinking necessarily about the implications of how to optimize it and make it as secure as it could be, and obviously as a result of that, mitigating as many of the risks as possible. So it's always good to step back and consider certain things before we simply do. So network authentication really is one of the many crucial elements, not the only one, but one of the many ones that we have to think about. Now, we've already talked about authentication. Drop the network piece, because obviously here in topic 8, we're focusing on network security. So yes, it should be specific to network and network design. But more broadly, back in topic 4, we spoke about identity and access control and identity and access management. And we spoke about the IEEE thought process, and authentication was front and center as part of our conversations there. So we've been through the logic of authentication, how it relates to in the process flow of someone providing their identity claims, how those claims are then going to be validated and verified through some sort of mechanism, a directory service lookup, perhaps a validation against an access control list, or perhaps against a series of potential things, properties, elements, concerns, context, and/or other areas that we focus on that will be vetted to ensure that the claim and/or the properties being offered by the, in this case, the subject to be able to seek authorization are legitimate. And then we authorize, we say yes or no based on what we see and what we validate, and then we audit. We track the use of, recording what is done to use that credential over the lifetime of that session. So IEEE is an acronym. The identify, authenticate, authorize, and audit thought process plays a central part here, even though it's happened way earlier in the show. And to that end, we've already spoken extensively about authentication. But keep in mind, as I suggested when we talked about it, and I'll remind you of here, all these solutions should be a one-size-fits-one as opposed to one-size-fits-all scenario. The requirements you have in your business may be very different from the requirements that another business has. That doesn't mean that we shouldn't think about IEEE generically as being able to be applied to both businesses, but it means the specifics of how IEEE gets translated into a thought process and ultimately into success in your organization may look very different than how it gets translated in another organization. You may have fewer users. You may have less resources. You may have certain specific peculiarities associated with your use of a certain resource that require a certain level of authentication or a certain minimum level of the ability to do certain things that others may not. There may be regulatory or statutory compliance concerns you're addressing. There's all sorts of variables, in other words, and we have to take those into account. As we think about one of the key areas that we focus on to drive authentication, 802.1x should come to mind, and hopefully it does for you as we're talking about this. Not to be confused, by the way, right, with 802.11. I have a lot of conversations with people about all these different standards and the capabilities associated with various implementation aspects. And I find a lot of people often confuse the 802.11 standards, plural, because there are many sub areas in that standard that allow us to talk about the specifics of wireless capabilities, right? 802.11 versus B, 802.11a rather versus B, G, and et cetera. Those are all individual solutions that allow us to understand how a certain level of speed and capability on a certain channel, a frequency, and a range for wireless transmission can be specified and can be implemented. Has nothing to do directly with 802.1x design, which is all about how we implement authentication and authentication security into our thought process around the network and the network design. So want to differentiate and understand that those standards are distinct and should stand alone and be individually recognized by you. When we think about designing for network security with regards to authentication, we want to make sure users as well as devices, this is important, right? Users as well as devices, meaning subjects in the language of access control, but also non-person entities. You keep hearing me say this, NPEs, right? So users and devices, computers, mobile devices, whatever they may be, are able to attach to networks where they belong and indeed have a reason to be there, but can only do so if they have successfully authenticated. That's really what 802.1x is all about. How are we going to allow them to authenticate and once authenticated successfully connect and be managed? But only if they can authenticate successfully. Very important to stress that and keep that in mind. Obviously, wireless networks are at the heart of this more often than not because a lot of this traffic and a lot of these devices are coming in more and more across wireless interfaces today. So we do want to note that and be aware of that. But this is not just a wireless thought process. We have to authenticate any user or any device connecting, whether they're on a wireless or a wired connection. So it's important to note that and understand that. So when we think about deploying solutions in line with 802.1x, what are we thinking about? Well, we may be thinking about the use of EAP, Extensible Authentication Protocol, for instance. And EAP, as we've talked about in some other episodes and other topics, although it is classified as, defined as, named as Extensible Authentication Protocol, P for protocol, it's not actually a protocol per se, but rather it is a framework that allows for extensibility, expandability, and the adaption of new technologies that can be bound to it. So we never just see EAP. We see EAP with TLS or EAP-TLS. We see EAP-MS-CHAP v2, as you see kind of right up there at the very end of that line, beginning of the next one. So EAP is paired with, bound to, additional solutions that will leverage the EAP framework and allow them to be integrated into our authentication thought process over time. Smart card use is deployed this way for the use of certificates for authentication, for instance, using EAP to drive that, as are many other solutions. So it's a very extensible and expandable container that allows us to add additional capabilities. That's how you should think of it as. And if we use EAP with TLS, for instance, as you can see highlighted, then digital certificates will be what we require the user and or the device to be able to present and have validated through the authentication and then authorization process, typically a lookup against wherever that digital certificate is going to be available to us to compare and understand whether it is legitimate or not. We would be looking, for instance, for the private key paired to the public key published in that certificate on file, typically in a directory service somewhere to validate it or move through the directory, or rather move through the certificate trust chain to be able to validate that that certificate has been legitimately issued. If it's coming from a third party, so we can understand that it should be used for authentication and accept it. There's a couple of different ways we could do that. If they're self-signed, internally issued certificates from our own directory service, we could look up and validate the key pair. If it's not, we would typically look up and validate the trust chain through a variety of mechanisms. And we actually talk about that as we talk about PKI in the earlier episodes in this topic, believe it or not. Where we use EAP, we could also see something like MSChap v2. That requires usernames and passwords as opposed to requiring certificates. Would probably be good for you to know the difference there. Also pick up on the fact that MSChap or MSChap v2, the later version of MSChap, is a Microsoft-specific implementation of CHAP, which is an industry standard and genericized protocol, challenge handshake authentication protocol, widely used and deployed across various operating systems and vendors, has been for several decades. But MSChap is unique to the Microsoft implementation, which means specifically you'd have to use devices that support MSChap or MSChap v2, and that may leave out certain infrastructure that will not understand how to interact with it. So again, we want to be thinking about these little things and understanding how to integrate them, right? Things that we also want to pick up on, just some vocabulary terms. We have what are called supplicants and authentication servers, keeping in mind that not all supplicants, not all, as I suggested just now, endpoints, users, and or devices will be able to support certain EAP methods like MSChap v2. And as a result, we have to understand that we may be trying to use something, speak a language essentially, right? Provide communication in a format that the other party may not understand or be able to work with. And so that can lead to mismatches and of course can lead to failure where we're expecting success. So keep that in mind. We should also understand that our authentication servers, wherever we're looking up and validating the claims that the user or the non-person entity is trying to make, those authentication servers are a single point of failure, but also the networking infrastructure that supports them and connects them to the rest of the system can also be a single point of failure. And people, again, often overlook this. They say, well, I have more than one authentication server. In the Windows world, for instance, this would typically be your directory servers, right? Your domain controller. So, well, I have more than one domain controller, so I don't have a single point of failure. If one of my directory servers or domain controllers fails, I have several others. They're all global catalog servers. DNS is Active Directory integrated, so it is fault tolerant because it's everywhere as well. And all of my core service infrastructure is resilient, highly available, and most likely fault tolerant in that scenario. So if I lose a domain controller, I have 10 others. I'm not worried about it. I can do lookups and authenticate users with no diminishment in capability at all. Great. That's cool. Awesome, right? I want to hear that. But then I'll say to you, great. So what does your networking look like? Are you redundant in your networking? Well, maybe. I don't even know if we are because I don't, whoever I'm talking to, I don't handle networking is what I'll often hear. I'm in charge of the line of business areas dealing with directory services and authentication of both local and remote users. We have a separate networking team is what I'll often hear that handles networking. I'm assuming, right, which are the deadliest words you ever want to hear someone say. I am assuming, right? That's right up there with I don't care and I don't know why, right? Because essentially they all mean the same thing. You have no knowledge of what's happening. You're just hoping that everything is going to go well. Not the place you want to find yourself, right? When things start to go badly. We assume the networking team has their act together. They're doing what they're supposed to do, right? They're using due care and due diligence, and they probably have built out redundancy in our networking fabric. That's a lot of assumptions, right? And at the end of the day, I don't want assumptions. I want verifiable proof. So when I talk about here, maintaining a failover VLAN for port switches that are connecting our authentication servers. What I mean is the authentication server itself may be fine. If the networking fabric experiences an outage because of some sort of chaos, we have to be able to still connect the authentication servers to the rest of the world through some sort of alternate pathway, or nobody's authenticating. Server may be up and running. Hypothetically, it is, right? Got blinking lights, looks like it's there, right? But if I can't connect to it, it's not answering the phone because the signal's not getting through. It's not doing me any good. So we often overlook one or more of these elements as we lay this out because another team is often responsible for this. So you have to take that into account as well. Good security is about good design all the way through the system pathway, the communication pathway, not just the piece you're responsible for. So what I like to hear is, oh yeah, we partner with the networking team. We have resiliency, redundancy, fault tolerance, and high availability, or some combination of those adjectives and terms associated with the entire communication pathway. If that authentication server stays up, but this main switch fails, we have a capability to fail over to another stack. If we lose this VLAN, we can port our authentication servers into a secondary VLAN easily. If this interface fails because this port on the switch were to fail, we can move to another interface very quickly. It's rare an entire switch fails, but it's highly likely by comparison that an individual port on a switch could fail, because that's typically what happens. An individual port goes bad, or an interface into the switch, the network adapter, if you will, right, the module will fail. And so you have to swap one or more of those out. A power supply can fail, but the switch itself is fine. You just build in redundancy in those various levels. So keep in mind the logic of that, because that's a place I find a lot of people tend to miss the opportunity to be successful. You may see that in a scenario on the exam or a troubleshooting issue that may come up, and you want to be prepared for that. And then finally, in this particular area of the conversation, I want to quickly, as we wrap up, talk about MAC authentication bypass in a minute. But also important, just before we do that, to note that we often see radius servers, and we've talked about radius in some other areas. We often see radius servers or something like radius, diameter, TACAX, TACAX plus, XTACAX, whatever that implementation of a radius-like solution may be. We see that, or something similar to it, in 802.1x thought processes and implementations, because remember, I talked about the fact this is about spanning the IEEE lifecycle, right? We're focusing on the first A right now for authentication, but that doesn't mean the authorization and the accounting are not equally important. And if you know anything about Radius and you heard us talk about it, Radius is all about accounting, right? It's about ensuring that accounting, keeping track of what that authenticated and authorized session, that user, that endpoint device is doing as they start and indeed continue to communicate throughout the lifetime of that session. So it is about tracking what is happening once we authenticate. And we don't want to leave that part out. That is so important, because we need information that's referenceable if we have to respond to an incident or have some sort of issue and concern down the road. We want to go back historically, look through logs, which is essentially what we're talking about, right? We want to find things like MAC addresses, as you see noted there, IP addresses, switch and port identifiers, protocols that were used, etc. All of that will come from our Radius capabilities. And if we're not taking that into account, we're missing a huge chunk of information that needs to be there. We could be great at doing authentication up front. If we're not tracking what you do once you authenticate, we have no clue what you're up to. You could be off and, raining chaos around the network. We would never have a good indication of that. Wes is laughing because that's often what he does when nobody's looking. I just think that's a heavy metal
song of Life for Networking, Raining Chaos or something like that. But that's where my mind went.
There you go. Right. There you go. Very cool. Got to get right on that after the episode. Right. All right. So finally, actually, no, not finally down there. Finally over here, what about MAC authentication bypass? This is also something a lot of people overlook or just simply really forget about and don't take into account. What happens if, for whatever reason, we find ourselves in one of those scenarios where we don't support the 802.1x authentication methods that have been specified? For instance, right, Wes is using a Macintosh computer. What if I choose EAP MSCHAP v2? He wouldn't be able to use that natively and be able to authenticate with that because his machine doesn't speak Microsoft, just to put it bluntly and plainly. So I wouldn't be able to see him authenticate successfully as a device. His computer could not authenticate. He would be able to authenticate as a user, potentially, because he could authenticate with the directory service using a username and password, but his machine could not authenticate. And let's just say that was the case, right, for our purposes of conversation. well, that would lead potentially to an issue, because we may not be able to manage his machine as part of an MDM, a mobile device management process. Remember back one topic ago in topic 7, we talked all about MDMs, right? And we talked about the ideas behind mobile device management. If I want to reach out with policy and manage his device, I need to be able to do so, maybe not using EAP MS Chat v2. I'd probably be using EAP TLS with certificates, to be honest with you, right? But just for purposes of our conversation, let's say hypothetically, we were going to do it with the EAP MS Chat v2 and his machine could not do it. The only way I could still allow the machine to authenticate and potentially be managed would be by using what's known as MAC authentication bypass. This allows network devices that are not able to use the specified 802.1x authentication method to still authenticate, because they have a unique capability associated with every one of their network interfaces or adapters. They have a MAC address, as in the media access control MAC address, as in the layer 2, sublayer in layer 2, MAC sublayer in the OSI model, MAC address, right? And if that's the case, we could take that MAC address and essentially create an access control list like capability where we list the MAC addresses that we're looking to have authenticate, and we simply do a quick lookup and a match and say, okay, yeah, Wes's MAC address is on this list. He should be authenticated. And that is what we call MAC authentication bypass. It allows us to determine that a device can still be authenticated and should be allowed to connect if it's not able to meet the normal specified, let's say, default higher level authentication mechanism specified by the 802.1x standard that we're implementing, in our case, 802, EAP with MS Chat v2. So we're able to then pass through the MAC address and authenticate with that. We obviously have to configure, as I note down below, the authentication server to make sure that it's able to work with MAC address-based authentication. There may be some settings or configurations, things like that, that may be unique to the implementation. So we just have to take that into account. But we want to make sure we understand that. A good example of where this actually comes into play is something we talked about a little bit earlier on in this show, or rather in this topic in the show, which is ICS, Industrial Control Systems, and SCADA systems, which are not going to have a full implementation of an entire operating system and fully qualified network stack that will support probably more recent versions of 802.1x authentication standards like EAP TLS. They don't have these devices the capability to work with certificates typically. So as a result, they're not going to be able to authenticate in these regimes. They're going to have to fall back on MAC authentication bypass in order to be able to authenticate and be managed. And so it's a great example in the real world of where we see this capability being deployed. Make sure you're familiar with it.
All right, ladies and gentlemen, as we wrap up this conversation on network authentication, please keep in mind that we got more to come. We want you to search in the library for upcoming episodes on implementing network or advanced network design. Thanks for watching.
Thank you for watching IT Pro TV.
Network topologies and software-defined networking, all coming up next.
You're watching IT Pro TV.
Hello, ladies and gentlemen. Thank you for joining us as we're moving through more of the implementing advanced network design. And helping us with this conversation is Adam Gordon. Adam, how are we doing, sir?
I'm doing well. Hopefully all of you are also. Always a pleasure to have you standing by my side here, sir. We are continuing our conversations in subtopic C in topic 8, implementing advanced network design. We're turning our attention to, as you can see over there, network topologies and SDN, software-defined networking. Hopefully all of you are fairly familiar with the standard network topologies. It is some of the assumptive knowledge we're taking for granted here as we get ready for CASP. If you're not, I'm going to quickly run through them for you. We're not going to spend a lot of time diagramming them out and really go into the detail of them the way we would, for instance, perhaps in Network Plus. And if you need a little refresher or primer, definitely go check Wes out over there in the library. He does a great job explaining all of these topologies to you in a lot more depth. But we are going to peel back the layer of complexity ever so slightly and ever so carefully around SDN. We're not going into a deep dive conversation on software-defined networking here, but we are going to lay out a very important element to help us understand how SDN not only can be applied when we're thinking about advanced network design, but to understand what it is, why we consider it to be an advanced element of network design, and things to look out for as we try to secure this particular approach to networking, especially in cloud and virtualized environments. That's what we're going to be focusing on. So as we begin our discussions around network topologies, hopefully items A, B, C, and D look somewhat familiar to you. They are the most common network topologies we often get asked about or see and hear about on exams. You should be familiar with them. No particular order here, by the way, but definitely want to have a sentence or two to say about each: a ring topology, a bus, a star, and or a mesh. Again, if you need a refresher, please go take a look at some of the other content in our library. You definitely can find it there. I will call out one important element about each just to remind you of the most salient point. With regards to a ring, keep in mind we often refer to token ring when we say ring, and the ring is going to look physically like any other network, but logically is going to operate in either a clockwise or counterclockwise direction, depending on how it is initialized. And you must have control of the token, the element that is sent around the ring, in order to send and to essentially grab control of that network long enough to get everyone's attention to allow you to send without being interrupted. So we just want to make sure you remember that. With regards to the bus, the most defining and important element there is the fact that all machines are connected to a common central line. We call that the bus line. And if any one of those machines is disconnected, turned off, or in any way does not have a complete connection, the circuit, we would say, is broken. And as a result, all machines on that particular line, that bus segment, will stop transmitting because none of them are able to send and receive unless all of them are connected and, importantly, turned on. So keep that in mind. With a star topology, we eliminate the likelihood for failure that the bus represents because the star introduces the idea of a connectivity element that allows us to centrally connect all those machines. We would typically call that a switch these days. And because the switch allows machines to be connected through a capability of binding one network card to one port on the switch with a network cable, and if we unplug either end of that connection, does not break the circuit because the circuit is maintained by the switch itself, not by all the elements connected to the bus line, we can send and receive and remove a machine from rotation without interfering with everybody else's capabilities. And with a mesh, we have complete redundant connections between and among all members of that particular connection circuit or area. So if we have 5 machines in a mesh, all 5 will be interconnected to each other. So item A will be connected to B, C, D, and E if we have all 5, and likewise all the others. Meshes are very hard to scale. They're very expensive and very problematic to scale, but they are still very likely going to be used. As you can see, there's a variety of use cases and places where we see them. In the modern world, we just often really don't think about them because we don't come across them as often. But site-to-site WAN links, for instance, are very often going to be deployed with a mesh topology. Devices in certain highly specialized areas and certainly highly specialized use cases like the military in the field, for instance, will often use mesh capabilities. Laptops that may be deployed for something like the one laptop per child initiative will use mesh topologies, as well as, believe it or not, citywide wireless networks, which a lot of people don't realize. If you're in maybe, let's say, a downtown corridor somewhere and the city government's providing wireless capabilities, that will be done with a mesh solution. Very expensive and very difficult to maintain. That's why we don't typically see them scaled very often. And any device that uses what is known as the Zigbee specification will be capable of being deployed and used in a mesh. You may want to pick up on the idea of Zigbee and mesh and linking those two together if you see them on the exam. All right, with regards to virtualized networks and then by extension, ultimately, software-defined networking, we've actually already talked about virtualized everything back in topic 6 as we talked about hardening the host, and we spent time specifically on virtualization and cloud more broadly. And we talked about virtualization being the ability to take resources, and we define those resources in 4 specific areas or categories: memory, so RAM traditionally, CPU, processing power, network bandwidth and network communication capabilities, and storage, actual ability to be able to move data in and out of a storage mechanism. We said those 4 areas are the resources that a host, a physical machine, will provide, pool, and make available for communal consumption to one or more what we call guest operating systems, or you commonly refer to them as virtual machines. So virtualization is simply just that. If we put the word network on the end and say we want to virtualize networking, we're focusing on virtualizing that particular aspect of the host resources and the capabilities, and then scaling that more broadly into the data center to virtualize not just the individual network connection that the guest OS, the VM has with a virtual network card, through the host in the physical adapter the host has, and then using that physical pathway out to the physical switches and routers and firewalls and networks that sit beyond, but rather we're going to extend that capability up and down the stack in the network infrastructure to virtualize the switches, the routing capabilities potentially, the firewalls and the protection capabilities and devices that create our gateways and our borders and our concentric rings of protection and our defense in-depth architecture. Load balancers would often be included there as well. Any and all of these become elements of virtualized networks because they can all be deployed physically or virtually today. And indeed, we have infrastructure that end-to-end is virtualized these days with networking. So virtualized networking is the idea of combining this hardware and software components in the stack together. We don't virtualize the cables, right? In the sense that the physical stack somewhere still has actual networking gear that we connect out to because the ISPs, the internet service providers, are providing physical circuits and connections for us to get in and out of our data centers. So there's still physical infrastructure somewhere in that stack, but the majority of what I just described can indeed be virtualized today. So keep that in mind, and allows us, when we add in the idea of software defining, because virtualized networking in and of itself is not the same thing as software defined networking. It is kind of a stepping stone to software defined networking. SDN, when we add it to the mix, is the idea of being able to automate the configuration through continuous integration, continuous monitoring, continuous management, oversee the use and optimization of that network, and then with the ability to have those things I just described, detect baseline drift and reconfigure and deploy quickly and very concisely if necessary. That's really where software-defined networking comes in. It allows us to be able to split the idea of networking and management of networking infrastructure into three distinct layers or planes, as we refer to them. And we could see them in the bulleted items that I'm just highlighting very quickly right down here, right? We see those three layers or planes defined. We split this conversation into what is known as the application layer at the top, also called the application plane. We split it into the middle layer of these three, the control layer or control plane, and then the bottom layer of these three, the infrastructure layer or the data plane. Now, I'm going to show you a graphic here in just a minute that kind of brings this all to life. But let's first identify kind of concisely what happens in these layers, because it's easy to say, oh, yeah, we have a control plane. But what does that really mean? Well, it's positioned centrally in the middle of these other two planes is actually pivotal and critical to its definition. But we have to understand what happens up above and what it is brokering in terms of conversation, movement, data, and capabilities to the area down below it to understand how it operates. So let's start at the top with the application layer. We think about the application layer or the application plane. What we're focused on here are network services, utilities, applications, etc. So essentially software and elements that are consuming and providing through software services and capabilities that allow us to understand how we want things to ultimately interact and to send that information through that application plane down into the layer down below, which will be the control plane. And this is where we specify ultimately, as we transition and move, how we want the requirements that we have to interact with this data, configure it properly to be translated. That's what the application layer helps us to do. In the control layer, or what's called the control plane, right here in the middle, right, we are thinking about taking information from up above in the application layer and now having it come down. And as it comes down, we determine how traffic should flow, how it should be able to move, right, from not just the application layer through into the infrastructure layer down below, but how it should be transmitted out of that infrastructure layer over time and then received and brought back up. So as we see bidirectional movement, right, up and down. This is fun, by the way. You should do this. This is
Something
cool.
like this?
Yeah.
Is this going to be the next exercise that we're going to
No,
be
it's
doing?
the SDN robot. It's the newest hot dance.
Mr. Roboto.
No, Mr. SDN.
Okay, very good.
And then I'm going vertically as well as horizontally.
It's going vertical.
That's
Watch
awesome.
it.
So when we determine how traffic should flow based on the status of the infrastructure layer, right, and the requirements specified by the application layer up above, what we see in the control layer is this conversation broker. It is taking stuff from the application layer and taking those requirements and translating them down, passing them down to the infrastructure layer where they're going to be acted on and implemented so that we can actually specify how that send and receive will happen and control what will happen as a result. And finally, in the infrastructure layer or the data plane, imagine again a 3-layer model. This is the very bottom layer, the bedrock or foundational layer at the bottom. So in that layer, looking up, we see directly above us the control layer. And directly above that, we see the application layer. And the control layer acts as this broker that is moving traffic back and forth between these 2 layers. This is where our infrastructure is going to be interacted with, right? So our network switches, routers, etc., as well as the actual data itself that is going to allow for the sending and receiving of data, the configuration of that infrastructure, and the data itself to be sent and received as we are sending it or forwarding it out to the appropriate destination is what we deal with here. So having said that, let's take a look at the first of 2 pictures I have for us, because I think they will be illustrative, hopefully anyway. And if we translate the application layer at the top, control layer in the middle, and down at the bottom, the infrastructure layer into a standard diagram. This comes from the OpenFlow and the SDN organization that is behind it, where we can see, this is kind of from their documentation, what we would see when we lay out a standard SDN topology. This is how it's defined. We see business applications up above in the application layer, and they're talking, as you can see, with some black bidirectional arrows right here using APIs, so software calls, into the control layer where network services are going to be able to understand this information and translate it so we can move it down into the infrastructure layer where we see icons that kind of represent connectivity and the connections between routing and switching that would occur. And so we see, hopefully, a graphic that our perspective brings to mind how these layers interact. It's very important to know what happens at each layer for the exam. It's very important to see the interconnectedness of these 3 layers and how information starts up above right here and gets translated into send and receive requests and the configurations that manage that all the way down below in the infrastructure layer. So definitely take advantage of that thought process and that image to keep it straight in your head. Now, what we want to add to this conversation are the architectural components associated with SDN. So we've just seen the 3 layers, right? The application, the control, the infrastructure. But now what we want to do is add the actual components and give names to them that exist in these layers and explain what they do. So that's the next part of this. And these are architectural components. And again, we'll explain them. And then I have a diagram that shows you what they look like to go with them. Okay. So SDN application, what's often called the SDN app, just generically. This will be that program that we saw that was labeled business applications, right? We see that up in the application layer. So the SDN app in that first diagram was just that yellow set of rectangles that said business applications. That's what it would have been. It's a program that communicates the requirements and whatever network behavior it expects it needs to have to send and receive to what's known as the SDN controller. The SDN controller is going to sit in the middle plane of the controller plane. That was the thing that said networking services and that, kind of blue rectangle that was in the middle of the diagram. And it's going to send that down via what's known as a northbound interface. The northbound interface would have been the black bidirectional arrows going up and down between the application layer and between the control layer that said API next to them. That would be the interface that was moving traffic back and forth. We call it a northbound interface because it starts at the top of the application layer, connects to the controller layer, and it allows for this bidirectional up and down conversation to take place, right? So we just want to make sure we understand the logic of that. The SDN controller translates those requirements coming down from the application layer down to what's known as the SDN data path. The SDN data path is a logical network device. We saw those down in the infrastructure layer at the bottom, the little black boxes with the white lines creating what looked almost like a mesh, linking them all together to indicate connectivity. Those would be the SDN data path elements that we're talking about, where we have a logical network device that's being defined. And then the northbound or SDN northbound interface, we just talked about that. That's the interface between the application layer and the control layer. But then we also have what's known as an SDN southbound interface. It's also referred to as the SDN control to data plane interface, which tells you where it is located between control in the middle and data down below, the infrastructure at the bottom. And it is sometimes referred to as the CDPI. This links the controller and the data path at the bottom. So let's go back to our picture here for just a minute. We kind of see all those elements as I was describing to you here, but it's a little bit hard to ferret them out here necessarily and really understand them unless we relabel some things and kind of close our eyes and imagine some other stuff is happening. So I've got another picture for us, right? And this picture here will help us to, because it's labeled a little bit differently, see the same thing, but see the elements we just described architecturally. And so we see here that we have some applications. These are existing without being labeled as such up in the application layer, the application plane. We have a northbound API right here that is allowing us to connect to the controller plane in the middle. And you could see this conversation would take place across this interface here. And then there's a southbound interface or API right here. OpenFlow is being used. And if you look here, you'll see OpenFlow is available right here on the diagram representing our southbound API and our southbound interface as well. And you'll see that we're connecting through that southbound API into our infrastructure down below for packet forwarding and for switching and whatever the case may be. So we're seeing all the same elements. They're just labeled a little differently here. So hopefully by labeling them differently and calling out the API or interface, APIs are just another way of talking about interfaces. By calling out northbound and southbound and labeling them inside of the appropriate relationship so that they form the buffer and the boundary between the application and the control and the infrastructure interface layer down below, you're able to see them in context. And hopefully that makes a little more sense to you. By using these elements to bring together all of the capabilities of SDN. And again, for the exam, you'd want to know what all those elements are, what they do. If you're shown an example in some sort of picture form, or if it's explained in a word problem or scenario, you have to identify the element. Definitely take the time to know what these are. You're going to be asked about them, right? But we want to make sure we focus on these and are aware of what they are. Now, the last little element or item here I just want to call out quickly because we're almost out of time for this episode. You know, a lot of people, if they do implement software-defined networking, and it's becoming more and more common today, virtualized networking in general is very popular in cloud environments, and as a result is becoming almost, I would say, the standard that we see in most modern cloud data centers as we scale infrastructure. More and more of this infrastructure is not only being virtualized, but is being software-defined up and down the entire stack. Storage, networking, a variety of different areas that we focus on. So SDN in particular can be vulnerable to security attacks or concerns and potentially vulnerabilities associated with the same kind of issues and concerns we have in normal, non-virtualized, non-software-defined networks, but also we have to be aware of the fact that these configuration elements that we create and that we use to automate deployment and that we use as we continuously monitor to understand drift, meaning hey, it should work this way, it's not, let's go and remediate, for instance, things like that, that these can be the focal point of an attack. And or if an attacker can gain access to these interconnections, somehow insert themselves inside the model. They gain control of one of the API interfaces. If they gain control of one of the layers, they can modify traffic, they can modify configuration, they can eavesdrop, they can do a man-in-the-middle scenario. They could do a variety of things that could lead to denial of service attacks. And so I talk a bit about this here and just call out that denial of service is probably our biggest issue. It's also the biggest issue in the physical, non-virtualized, non-software-defined world. But although it's essentially for the same reasons, because we're not software defining, we're more concerned about someone gaining control of the device as opposed to the layer. It still boils down to the same thing. Somebody hacks our router and reconfigures our access control list or implements a change in the password and then changes the configuration, we have a denial of service event on our hands. It wasn't because of a software-defined element. It was because somebody hacked the physical infrastructure, but we end up in the same place. So understand that just because things are virtualized and software-defined doesn't mean they behave that much differently. They often are still going to fall prey to, be susceptible to, almost identical kinds of attacks. We just have to adjust slightly to understand where that attack vector may be most likely to be successful.
All right, ladies and gentlemen, that's all for this conversation, but we still got more when it comes to implementing advanced network design, so we hope to see you there, and thanks for watching.
Thank you for watching IT Pro TV.
Advanced network design, time for some review. Stick around.
You're watching IT Pro TV.
All right, ladies and gentlemen, get your notes, pens, and papers ready. It's time for review. Adam, lead us off.
Ta-da!
And that's been a great episode.
All right. I got more to say than that. I do. Ta-da twice. That's what I wanted to say.
You got two of them? Okay.
Ta-da squared.
Okay.
It's
Sure.
also commonly referred to as Dada.
All right.
That's the shorthand. Join me here. We are doing one of our famous review question episodes. And if you haven't seen them before, boy, are you in for a treat, because it gets a lot wackier from here than it has been so far. What we do with these episodes is we give you some review questions, not because we want you to guess the right answers. We tell you what they are. Hopefully that'll help you to study, certainly. But really the goal is for us to break down the methodology of how to answer a question like this when you see it on the exam. Not these questions, but questions of a similar type. We're told we have to say that as a disclaimer, just in case one of these questions does actually make it on the exam. You didn't hear it from us first. All right, but you're not going to see this exact question, but you're very likely to see questions like this. And what we do individually and collectively, because we chime in individually and collectively here as needed, we talk about the methodology, but in some cases, we also give you some information in terms of pulling out keywords and indicators, hints, and things that help you to be successful on the question. So hopefully we could do that here. We'll see how we get down the road and how successful we are. Question 1 of 3, by the way, because we do have 3 for this one. First one, this is one you will often see, a multiple answer question, meaning select perhaps more than one answer that may be right. We're told specifically that we have to select 3. So that's going to be important, because instead of saying choose all that apply, where it could be 1, it could be all, it could be anything in between, we are being told specifically how many of these answers we have to choose in order to answer the question. Correctly, obviously, if you choose the right ones, but correctly or incorrectly, you have to choose 3. So first thing to be on the lookout for will be obviously that we can choose 3 that seem to make sense and do seem to be correct. So just keep that in mind. Now, which of the following are, and this is the key statement in the question, advantages that IPv6 may have over IPv4? Well, I said these specific things as we talked about IPv6 back in our remote access and IPv6 episode. I told you it had a much larger address space. Right? We went from 32 bits to 128 bits. I told you that it had built-in encryption support. I even told you that it mandates you use IPsec, right? And I told you it provides for greater network management efficiency. So I specifically talked about all 3 of these elements, and these are, of the 4 listed, the 3 that are going to provide advantages. Backwards compatibility, I specifically said that it is not going to provide backwards compatibility. Indeed, we devoted the better part of our IPv6 episode to talking about the bridging technologies that allow for us to use IPv6 with IPv4, because it does not provide for backwards compatibility in and of itself. So that's the exact opposite of what we talked about. So if you paid attention to that episode, you would have been able to answer the question correctly either way. The trick is picking up on the statement that implies what should be driving the right answer. In this case, it's really just a matter of knowing factually the identified elements that we talked about that would form the body of the right answer, but also picking up on the fact that we must correctly identify 3 elements in order to answer this correctly, or to provide a correct answer on the exam. This one's relatively straightforward. All right, what about the next one? System administrator of MyITproTV is planning on setting up a VPN that enables some sort of remote access for people working from home. Okay, that's pretty straightforward, pretty common business need. As a cast, which type of tunneling protocol would you be recommending the VPN employ for optimal security? Now, on the surface, this question sounds pretty straightforward. The right answer, of course, as you can see, would be L2TP with IPsec. But let's break this down. The first part of this question, the entire first sentence, really doesn't matter to us. It's actually totally irrelevant. You can throw it away. You could still answer the question correctly. If I just said the question was going to be this would not change your answer in any way, nor would you hopefully not come up with the right answer? In other words, nothing's changed. What I'm pointing out to you is on the exam, if you could filter out the statements that are just totally irrelevant, that get in the way, that distract you, you're much more likely to focus in on the things you need to know, right? And then we could see, well, we're really being asked tunneling protocols. Okay, well, I look at the list, looks like they're all pretty much going to be tunneling protocols. Would I recommend that a VPN employ for optimal security? Well, there's kind of a suspiciously vague term, optimal security. That could mean a lot of things, right? And I'm just going to do Control Z here to put back my first statement so it's in the notes so you actually have it when you look at the notes. But optimal security, let's talk about that, right? VPNs that employ optimal security using tunneling protocols, right, as I highlight here. That's really what we want to figure out. Well, of all the protocols listed, which one of them is going to provide not just a tunneling capability, not typically associated, or rather typically associated with the VPNs, tunneling capability associated with VPNs, but optimal security? Well, the only one on there that provides anything like an optimal security configuration would be L2TP with IPsec. L2TP by itself does not provide any security at all. It simply provides a tunnel that is not encrypted and is not authenticated, which means we really don't have any additional benefit. We could just send in the clear without a tunnel, and we would essentially be doing the same thing. So you never see L2TP deployed by itself, and it's never the right answer. It's always going to be paired with IPsec if you're not already familiar with that, right? Point-to-point tunneling protocol, right? Well, that's okay, but is it as good as L2TP with IPsec is what I would ask myself, right? In other words, it provides better protection than L2TP. It provides better protection than the the PPP protocol, right? But because it's not sending in the clear, right? So obviously it's going to provide better protection than that, but it's not going to provide as great a set of protection elements or as optimal a set of protection elements as L2TP with IPsec, where we can use encapsulating security payload, ESP, and authentication headers AH to be able to bring those security protections to bear. So of the answers there, the only one that's really the best answer that stands out, even though we're not asking the question that way, what we're really asking you is, instead of optimal security, would you choose differently if I said choose the best possible tunneling protocol that will provide the most security for us, or something to that effect? Then L2TP with IPsec would hopefully stand out for you, right? But we didn't ask it that way. We said optimal security. We're implying we want the best of the four. You have to figure that out and answer the question accordingly. So hopefully that makes sense to you in terms of dissecting that particular question. And then finally, this one's a little bit longer. It's got a really long setup. It's got a whole bunch of options for the question. I've actually even got a little hint for you about some information you may not realize down below that helps to explain why the answer is correct. But let's start with the question, because it's a paragraph. It's a long, long question, right? All right, so MyITproTV is thinking of implementing technologies that use IPv6. Okay, read that. Great to know. Let's see what else we got. As the admin of the network that's going to plan for the project, or rather as the admins start to plan for the project, they are concerned about which transition technology would be best to deploy. Okay, so they realize they need some sort of transition technology. At that point, my mind and my eyes go immediately to the answers. I'm looking for any of those answers that may not be an accurate and real representation of transition technology. If I find one, mentally I've eliminated that one already, and I'm not even going to look at it, right? Now I quickly scan and see 6-4, I see Isotap, I see Teredo. Okay, nothing I can eliminate right off the top, because all of them in theory potentially, so far, only given 2 sentences in, fit the bill, because all 3 of them are transition technologies. They have very distinctly different usage profiles, as I keep stressing to you. But so far, check, 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 all of them in theory would answer the question. But we know it's not going to be that simple, right? All right, so then we keep going. The areas that they are concerned about and that they are needing to provide for deal with NAT traversal and tunneling of IPv6 traffic over the existing IPv4 network. Ding, we have a winner. That right there is what they call the money statement, right? That is the heart of the question. Coincidentally happens to be in the middle of the paragraph, but it is the heart of the question. That right there should immediately allow me, as it does when I take a test, to go down once again, scan the answers. And now if I've got my facts straight, I should immediately be thinking there's only one possible set of answers here that I should be considering. And it starts with the word Teredo. And if Teredo is not in that set of answers, I don't want to see it again. So when I look, knowing that Teredo does tunnel, but also does nat traversal, as opposed to 6-4, which tunnels, but doesn't do nat traversal, and isotap, which doesn't do nat traversal either, which means I can eliminate 6-4 and isotap immediately. Well, that's really convenient because I have 1, I have 2, I have 3, and I have 4 of the 6 possible answers that I've just eliminated. So I went from having to figure out how many of these may be right, choose all that apply, it says at the end, to now, at best, having to only choose from 2. I like those odds, right? I just improved my chances dramatically if I'm not sure of the answer. So I immediately eliminate those 4 answers and I only start focusing on the 2 that say Teredo. Now, if you don't remember that Teredo provides nat traversal as well as tunneling, well, then you've got a problem on your hands because you may or may not be able to pick up on the right answer. I always remember because I think T for Teredo, T for tunnel, right? And T for nat. Kind of a triumvirate there of T's, right? That's how I remember it. Wes is not shaking his head yes, so he doesn't remember it that way. He's actually holding his head in his hands going, what are you saying?
Now, one of the things I'm thinking through this whole entire problem here, or question, Adam, is your stewardship of your time. You know, how to get to that answer really quick. Really, really good advice, because you have to keep an eye on your time. And these tips are invaluable, very valuable, when it comes to the, getting through the test.
Just getting rid of all the fluff, right? Because you want to focus only on things that are going to add value by giving you an option to answer correctly. All right, so we picked out the money statement. We know we're focused in on Teredo. So let's highlight those 2 for just a minute while we're just finishing up here, right? All right, and then we go through and we keep reading. As a CAF, our concerns are focused around functionality as well as risk mitigation and concerns about that. What transition technology and countermeasure would you recommend? Choose all that apply. Nothing that really changes our thought process in the last couple of sentences. It's still all about Teredo, right? Nothing has changed. The only thing that we need to add to that is choose all that apply. Now, remember, it doesn't say choose 3, doesn't say choose a certain minimum number. It says potentially choose all 6 if necessary, because maybe all 6 apply. Well, we've identified clearly that only 2 of the 6 possibly apply. And of those 2, we don't know if both are correct or only 1 is correct, right? So now we got to do the homework to figure out exactly which of these 2 is going to fit the bill. Now let's go back to our thought process. Let's read both answers, by the way. It says here, Teredo with packet inspection to allow for malware detection. That happens to be the right answer. And my explanation right down below here tells you why in just a minute. And or Teredo with outbound IPv4 UDP traffic blocked at the firewall. Now, if you're not familiar with the nuts and bolts of Teredo and how it works, then you may not pick up on the right answer here, right? Because it's not obvious, but you need to know what I wrote down here in order to understand this. Let me just actually make that a capital. When you set this up, right? The problem we run into when we do nat traversal, and we use Teredo specifically as the technology to tunnel the IPv6 traffic in the IPv4 stream to get it through the NAT device, essentially allowing it to pass, right? You shall not pass, right? I feel like Gandalf standing on the bridge when the Balrog's about to do battle with him. You got to be a Tolkien fan to get that reference, I suppose. Outgoing UDP packets to port 3544 have to remain unfiltered, right? This is an issue because the problem becomes that if we are filtering that, we get an error in the Teredo setup and we are not able to actually send the traffic through successfully and tunnel it because Teredo assumes that that port and that protocol will be available and that it won't be able to move through the NAT system. And so when that is blocked, or as the answer of the second of the 2 answers on Teredo implies, Teredo with outbound IPv4 UDP traffic blocked at the firewall, that essentially breaks the Teredo adapter capability, prevents it from being able to tunnel successfully, and renders it inoperable. So you may not know that. That's why I wrote the definition explanation out for you. But of these 2, because of that requirement, the only one that's possibly correct is the fact that we would use Teredo with packet inspection. So we could see malware in the stream, but we're not actually blocking the outbound UDP port protocol mapping that allows Teredo to successfully connect and move traffic through. So this is a difficult one because unless you're familiar with Teredo, you wouldn't probably know that. Take note of it for the exam in case you see it so you're aware of it. But this is something where you have to have a little more knowledge of something a little bit esoteric to answer the question correctly. You'd probably get it down to the two answers, but likely what would you choose? You may choose that both Teredo items were correct, tricking you into answering the question incorrectly, even if you filtered it down to know what the technology was that would be needed to theoretically answer correctly. So you got to pay attention to the subtle details here.
All right, ladies and gentlemen, that last question, I have to say, it's worth its weight in gold, or, for Adam, worth its weight in espresso. So thanks for watching, but keep in mind, we've got liquid gold. That's right. We've got more to come in CompTIA's Cast Plus, so we hope you join us there.
You're watching IT Pro TV.
Network security controls, concepts, and vocabulary coming up.
You're watching IT Pro TV.
Hello, ladies and gentlemen. Thank you for joining us. More concepts and vocabulary coming your way via this gentleman right here. Hello, Adam. How are we doing, sir?
Doing well, doing well. Hopefully all of you are also. We're moving into subtopic D in topic 8, so we're getting near the end. We have a few things left to do in this subtopic. And remember, our Key Points episode is coming up along with a cool hands-on demonstration towards the end of this conversation, talking about how to implement network monitoring with NTO-PNG. So that'll be cool. Join me here. We're going to be starting with network security controls, concepts, and vocabulary, one of those famous episodes we do where we lay out terms, ideas, and thoughts that are really going to help shape and drive the rest of the conversations in the episode. Now, unlike the way I do a lot of these episodes where we tend to break out in a PowerPoint, put our vocabulary there, let you follow along with it, we're going to stick with the notes in this one. The concepts are pretty straightforward and things we've already discussed in many other areas, but I am going to use a diagram to kind of bring them all to life and show you where we would see them logically and physically appear after we get done defining them. So a slight take on a variation here, but we're still going to be able to bring in all of the important points. All right, so let's get started. Oh, and of course, it would be helpful if I actually went back up to the top of my notes for this episode so we could get started properly. There we go. I thought I rolled back up to the top, and I must have not. So when we think about vocabulary, concepts, ideas, and things we want to focus on with regards to implementing network security controls, not necessarily the first thing that jumps to mind, but the first thing I'm going to mention, because it sets the stage for many of the other things we'll discuss, is the idea of network baselining. We've talked about baselines before, the ability to be able to specify a certain configuration or a certain specific way of seeing or doing or understanding something, and then measuring against that baseline that specified standard to ensure that everything is compliant, is aligned with, supporting of, and indeed configured in the same way. And if there is drift, if there is a change, that we can mark that, understand that, be alerted to that fact, and most likely take some sort of remediative action, changing, modifying, putting back into compliance, whatever may have drifted. And so the idea of a baseline in general is very important because it gives us the opportunity to create stability and standardization in our thought process, in our infrastructure, and by extension, with our expectations around how we can create normalcy, but also the expectation of how we minimize risk. And all these things become very important, reaching all the way back in many respects to some of the earliest topics we talked about back in, or episodes we talked about back in topic 1, as we talked about risk and governance. And we see this as a theme in every topic up until now, that ability to minimize through standardization and management of expectation the risks we may face, and to maximize our opportunity to be successful at dealing with them is really what baselining presents for us. Put the word network in front of it. Well, it's pertinent to our discussions in this particular topic. We're really focusing on network security. I could have easily said host baselining. That would have been appropriate in topic 6. Could have easily said baselining for mobile device management. Would have been appropriate back in topic 7. Could apply, in other words, this thought process to any of the areas we've talked about up until now. So keep in mind the idea of a baseline. We've talked about them before, and I'm sure you have familiarity with them. We're going to apply that concept along with several others to our diagram here in just a couple of minutes. What about configuration lockdown? People often confuse configuration lockdown with a baseline and say, well, we have a baseline, we've locked down our configuration. I hear that from customers all the time. Yes, unfortunately, how we often tend to use these terms, people do confuse the two and they do seem to conflate them and feel they are going to be indeed one and the same. But in fact, we're really talking about two different aspects of something. Configuration lockdown, as I point out there, implies that we have change control associated with our configuration. We're not going to make changes to that system once it is installed or once we apply the configuration unless we have some sort of authorized ability to do so. That's where change management typically comes in. And as I note, configuration lockdown can actually be applied in such a way that it blocks administrators from making unwanted changes accidentally or purposefully as well. Network baselining, or indeed just baselining in general, is the idea of creating that standard we want systems to approach and ultimately be managed via as we implement that standard across the organization. Locking down that configuration says we're going to take that baseline, apply it, and then make sure everybody adheres to it, and that we will not allow deviation. And if we do see deviation, we will immediately address that deviation. So it's kind of the next step in what the baseline is going to represent for us when we think about configuration lockdown. I'm getting the high sign from my co-host here that he's either got to go to the bathroom or he needs to say something.
All right, so I'm going to... No, actually, do we see signs of this?
You gave me the number one, then the number two, so
Yeah,
I wasn't
absolutely.
sure what that mixed message might be.
Yeah, I won't repeat that statement.
Okay.
Absolutely. But, some of the things I think, and I know we're vendor agnostic here, Adam, do we see some of this stuff like maybe manifest itself in, so maybe an administrator has pushed out a GPO? Because one of the things I'm thinking is when you go to certain settings within a Windows environment, it says some of these settings are actually configured by your administrator. So when we're implementing something like a group policy object, are we seeing aspects of this?
GPO.
I defined it too.
You did after I put the cup up.
I did.
Saw me
Absolutely.
put it up.
Good peripherals.
Yeah, that is good. That's important. So it's a good example, actually.
Yeah.
I like that example a lot. So potentially being able to push out one or more settings, right? Whatever it may be, perhaps combination of them through a group policy object, and then applying that change is one aspect, right? And we, in theory, could create the baseline from a setting or a collection of settings in the group policy object. Think about it that way.
Sure.
Maybe it's not a configuration baseline in the sense that we're modifying specific settings that are unique to the computer. Remember, we have both user and computer options in a GPO. So yeah, in theory, we could do one or the other. We could remove certain icons, perhaps block access to the command line, for instance.
Sure.
We could enable or disable software-based functionality for things like Internet Explorer or whatever the case may be. So yeah, we could definitely do that. And then through continuous monitoring, we can be alerted if there is deviation from that. Now, the GPO mechanism itself, by itself, doesn't give us the ability to be alerted necessarily when there is a change.
Sure.
And it doesn't tell us necessarily that the system is perhaps out of compliance. We have to add some additional software capabilities to it. So a configuration management solution like System Center, Config Manager, or in the Microsoft world, or any kind of configuration management solution, vendor notwithstanding, would give us that capability. So yeah, if we pair the two together, we can actually achieve the same exact thing. So I like that a lot. It's a really good way of thinking about it. All right. So that was the 1 + 2 = awesome answer.
All right, very good.
All right, so I like that a lot. That was good. So what about change monitoring? Yet another aspect, another link in this chain that we're talking about, right? The idea of change monitoring is the idea of understanding if a change has occurred, as we've implied is the case, and then having some sort of mechanism that will alert us, that will tell us that this is going on, allowing us to log it, allowing us to be alerted to that fact, maybe even allowing us, as I suggested, to take some sort of remediative action, correcting or clarifying what that change is, who initialized it, was it authorized? If so, why is it occurring outside a maintenance window? There's all these things we'd want to know, right, potentially. Availability controls. Part of our baselining procedure should also include our ability to understand how to create resiliency and resistance to failure in our infrastructure. We talk about defense in depth. You often hear me also remind you that availability in depth is equally important. And so things like uninterruptible power supplies, redundancy in and around and across our network, and other areas of infrastructure, but we're focusing here on networking. Load balancers are a good example of that. Multiple switches, routers with redundant power supplies, right? All the things you've heard me talk about or will potentially think of on your own would all be examples that would be part of this here. We're really talking a lot about different elements. We're kind of cherry picking them and bringing them in. But all these elements together are part of how we can think about the vocabulary, the concepts associated with the idea of creating not just security, but common sense approaches that allow us to create redundancy and availability, which also leads to stability and ultimately leads to security. So very important to think about that as well. All right, what about network access control lists, ACLs? An ACL is really just a list of people or IP addresses or whatever the ACL may use as its reference point to understand who should and or what should or should not be allowed. It's a list of allow these things and don't allow these things. It's really what an ACL implies, along with perhaps some level of access. Allow this person to have this level of permission or access while this person only gets this level, right? So whether it's a person, whether it's a non-person entity, a machine, using an IP address or a MAC address to show up and prove who they are, we don't really care about the specifics. We care about the idea that we can apply the same concept of access control that we talked about in topic 4 for a resource, a file that has an access control list with a set of users or groups that are assigned permissions. We do the same thing with network infrastructure. We can have an ACL at a router, as you've heard me say before, allowing or disallowing people to connect into and through the router based on the IP address that they present with or the MAC address, or maybe a combination of both, depending on what we decide to do. So as a result, we want to think about how we can implement that kind of a solution. Also, it is going to come down to ultimately probably thinking about focusing on perimeter or gateway devices that exist in a perimeter like a DMZ. We'll take a look at this in our picture here in a minute, and being more focused on ACLs associated with access in those areas where we may expose those systems to the outside, because that's really where we have to focus long and hard, really think carefully about the layers of protection that we incorporate and create and envelop this device with, so that we have this multi-layer defense in depth idea that comes to life. If I have a device buried somewhere deep inside my network that never sees the outside world, and is only accessible by a small handful of authorized people inside, perhaps on a air-gapped or logically gapped network in a VLAN on a separate infrastructure switch used for QA and testing, I'm not really going to be overly concerned about putting a network ACL in place because I've got other protective measures that prevent people from coming in. But if this system, like a web server, for instance, or another resource, sits in a DMZ, and I'm concerned about certain people gaining access and blocking others, then yeah, a network-based ACL in some sort of a gateway device would be an appropriate way to think about that. And then finally, the DMZ itself, as you've heard me talk about, is the physical as well as logical area of our network infrastructure that we create either using multiple firewalls or gateway devices, or only one perhaps that is multi-homed, as more than one network adapter to connect to different network segments logically as well as physically. And when we do that, we can place infrastructure in this in-between kind of gray area that is not inside of our network totally, but is also not fully exposed outside of our network. It sits in an in-between zone where the LAN is clearly on one side, the WAN is clearly on the other, and we have the in-between, right? Where it is not quite LAN, not quite WAN, and we can allow infrastructure to be exposed both to the outside, the WAN, and the inside, the LAN, but do so from a safe, neutral area where we can create logical and physical breaks to prevent just straightforward traffic flow that's not impeded by any sort of control or countermeasure mechanism, and hopefully as a result, build borders and walls that are strong enough to keep the bad things out, but allow the good things through. So let's bring this to life and talk about some of these things by looking at a diagram, or essentially a picture. I have here just a generic diagram that clearly shows the DMZ. So that part's pretty straightforward to figure out. It's labeled right here, the box on the right. Inside the DMZ, we appear to have a single machine labeled as a web server. There are two firewalls on either side of the DMZ. Let's call this side on the right-hand side of the diagram where our user is over here. Let's call this let's call this the WAN. This will be the external outside area. Let's call this side on the left where we have a connection back into what looks like some additional computer resources. Let's call this the LAN area, the local area network on the inside, right? So that way we can just differentiate, and I'll label those areas of the network for us here. So let's just call this the LAN, and we'll call this side the WAN over here. Normally, we have a cloud in these diagrams to represent the WAN more often than not, as opposed to just, a user. So, if a cloud makes more sense, and that works for you. We'll put a cloud over there. Looks like a malformed thought balloon that's coming out of her head over there. All right, so that indicates the WAN, right? The WAN level connectivity. So in the DMZ, in this area in the middle here where the web server lives, right? Let me just change my color. Let's go to purple. So in this area inside the box, but specifically, right, let's say in this area between the two firewalls, this is where we could begin to see some of the application of the controls and the vocabulary concepts we talked about. We could, for instance, use a baseline to set this web server up, and we could use configuration monitoring to make sure that that web server stays set up the way it is supposed to, and we can make sure that if there's a deviation from that baseline that we're alerted to it, right? So we could apply a baseline here. So let's go ahead and put a baseline in place. We'll go ahead and we'll use kind of a brown marker, and let's just say that our baseline, right, BL for baseline, gets applied to that machine. And in addition, right, to the baseline, we also want to have some sort of monitoring capability and alerting capability. So we'll put monitoring and alerting in here also. MON for monitoring and AL for alerting, right? I will just kind of draw there, and all that could be applied there. But could we equally and easily turn that baseline and that thought process of that baseline along with that? I'm just going to make like a little squiggly to incorporate all that. Could we put those onto any of these systems down in here inside the LAN to the same effect? We certainly could. If you think about it, it would easily be applicable. The baseline itself may not be applicable because maybe the baseline is specific to a web server, and maybe these are different machines and maybe they're not web servers. So maybe we would create a different baseline, but the idea of using a baseline to configure those systems, continuously monitor them, have some sort of change control and alerting capability if something were to deviate from that expected baseline and behavior is applicable regardless of what the machine itself may be doing, right? What about the user out here and perhaps the infrastructure that user is going to be interacting with and potentially even using, although we don't see a computer here, on the WAN? Would we apply any of these countermeasures, these controls, these mechanisms? Will we apply them to this user outside? Think before you answer, because the obvious answer may not be the one that is the correct answer. You would very quickly most likely say, well, no, right? Why would we do that? We don't have infrastructure that user is using. We're not controlling them. They're coming in from outside without being part of our network. But are they? What if they're a remote user that actually works for our company? And what if, as a result, they're coming in on some sort of secure connection? We've talked about VPNs and things like that. However they connect, really not important right now. We know it should be encrypted, whatever they do. But let's assume they're connecting from home and they're just working as a remote worker. Would we want to reach out with a baseline, with monitoring, with configuration management, continuous monitoring and alerting to that endpoint and monitor it? If it's corporate-owned asset, absolutely. Of course we would, right? Everything we talked about in topic 7 tells us that mobile device management can and indeed should be extended to those remote workers, and we should control those laptops, mobile devices, whatever they are. What if it's a user that is using a personally owned device but accessing corporate infrastructure to see email? Well, I want to access that device and own it and control it in some way. Maybe we differentiate and split that device down the middle, as we suggested in topic 7, where we can leave the personal information and personal things like pictures and videos and whatever that you have on your phone that are yours, separate from the area where we put in the configuration and control the email settings and whether or not the email stays on the phone and what you can do with it. And if there's a problem, the phone gets either lost or is compromised, we can reach out, we can wipe the corporate side of that device, leaving the personal side potentially intact. Maybe even wipe both if the user says, I don't know where it's gone, I prefer everything to be destroyed, then potentially have somebody get their hands on it, and maybe we'll just remotely wipe the whole device. So the logic can even be extended, right, out over here into the WAN, even though we don't see a device, but let's just hypothetically put a computer or something there, we should be able to extend the logic of that out to that set of users, those sets of devices as well. The only time we really wouldn't apply this logic is if that user is a guest user that we have no connection to, a customer in theory, coming in to our e-commerce web front end. Let's say you're going to Amazon and you're looking to buy something. Amazon is not going to reach out and try to apply a configuration baseline to your machine, at least not yet. Perhaps when they buy the rest of the planet, maybe that will be the case. But for the moment, Jeff Bezos has no outwardly, evil intention or designs on your desktop device, at least none that we know of anyway, right? But will they push advertising? Will they push cookies? Will they push other things down into that device that allow them, in theory, to control aspects of what you see? Not how you do it, not what you do, not directly anyway, right? But can they manipulate certain aspects of the device? Indirectly, they could put a cookie there. They can launch advertisements to you based on preferences that are recorded as you shop to understand what you may want to see the next time you show up. They've proved to be masters of that, right? Hands down. So indirectly, they're manipulating aspects of the device, but not the same way we're talking about, and certainly not with the elements we're talking about here.
All right, ladies and gentlemen, that's all for this episode, but keep in mind we got more to come in implementing network security controls, so you're going to have to come back and check those episodes out. Thanks for watching.
Thank you for watching IT Pro TV.
VLANs and network data flow, all coming up next.
You're watching IT Pro TV.
Hello, ladies and gentlemen. We are continuing through implementing network security controls, and here to help us with this conversation is Adam Gordon. Adam, how are we doing, sir?
I'm doing well. How about you?
I'm doing good.
Awesome, awesome. I see you're all set with your tailgate going on.
Absolutely.
Right,
we got some football in the background there. You got it.
You're like all set. You're going to turn around. The minute I start talking, you're not going to see Wes. If we go to him randomly, you'll see the back of his head is going to be watching football.
That's right.
You brought the tailgate supplies?
Yeah, yes, I do. We got some chicken wings for after.
He's got his easy chair and his little cooler set up. He's got quite the rig off camera
Barbecue.
here. All right, so we are jumping in to our conversations around how we implement network security controls. Remember, we're in subtopic D. But remember, we're talking now not about the security controls, concepts, and vocabulary. We just got done with all that. We're moving into VLANs and network data flow. Now, VLANs, right, virtual local area networks, are going to be something that I find a lot of people, I guess, maybe struggle with would be a good way to think about it, right? And, I often think about the fact that while the concept is pretty straightforward for the most part, I think it often is the gap that people have with it that nobody's really taken the time just to show them a picture and explain to them the idea. And so we're going to use a picture to help you understand VLANs along the way. We're going to focus on the use of VLANs as potentially a network security control. You've heard me talk a lot about them. We're also going to talk about network data flow and just how important that is in terms of mapping out and understanding visually what our data is, where it comes from, where it has to go to, what makes it up, but then also the tools we can use to create, understand, and track those data flows. I'm thinking NetFlow. I'm thinking tools like that we may or may not be aware of and that we want to understand a little bit more about. All right, so when we think about network segmentation and virtual LANs or VLANs, what we're thinking about is grouping hosts together based on a number of factors. Traditionally in a VLAN, we're thinking about a VLAN ID, a numerical identifier that's usually called a VLAN tag. That is assigned. The question is, where is it assigned? Do you know where we assign VLAN IDs? I know. Wes knows. If you saw our intro little thumbnail picture, you probably can take a hint from that. We do assign them at the switch. Most people don't realize that, or if they do, they don't stop and think about the fact that that is where we would have to manage them and assume that they are created also and obviously deconstructed if we need to remove them. Especially important in virtual environments where the switch is a virtual element along with all the other virtualized network infrastructure. We still assign virtual LAN IDs there, but we have to have a management interface that is part of the virtual appliance, the virtual switch itself, to be able to do so. This is usually a command line option more often than not as well. So when we think about VLANs, we think about the ability to logically isolate and segment our network as opposed to physically isolating and segmenting our network. People often confuse VLANs with subnets, which essentially is what I just said, right? Logically isolating our network and segmenting it is a virtual LAN ID that puts you in a group, and you're essentially in a membership scenario where you're in that group with that ID. If you have that ID associated with your group membership, you're able to access resources that are also in the group. The VLAN ID, in other words, indicates what resources in what group you should be able to interact with. If you have a subnet associated with your networking, we usually will have a subnet mask associated along with our IP address within that subnet range, and more often than not, a default gateway if we need external access. If we have a subnet mask, we are creating a smaller or perhaps a larger block of IP addresses, depending on how many addresses we put in, whether we are customizing that subnet mask or not, and we're associating all the IP addresses in that block with each other. Can we be in both a subnet, perhaps a large grouping of IP addresses associated together, and have access to resources that are on different switches as a result of that? Yeah, the switch is really not the issue associated with an IP address and a subnet mask. We have to worry about whether we can get to the machines that are in that subnet. Are they on the same LAN as us, the same local area network, perhaps on the same switch or not? Really would be irrelevant as long as they're connected to each other. If I have to cross over a boundary that demarcates one network from another, a router traditionally would be that boundary in this conversation. I have to have a default gateway, as I indicated, associated with my ability to move through that router to see resources somewhere else. So we can physically segment and isolate and chop up our network. We can also logically isolate and chop up our network. And we're talking about the distinctions, but also the capabilities associated with that here. Also keep in mind that if we're using VLANs, we're logically isolating resources that are typically on the same switch from each other. We're not using a subnet to do so. We're using a numerical identifier programmed into the switch to create micro groups that we become associated with. Let me show you a picture of what I mean by this, just to give you an example. Let's assume, hypothetically, we had 4 VLANs, just like the ones you see in the picture here, laid out. The device in the middle that's kind of, going out to each of them with the lines to open them up would be our switch, right? That's where we would see, theoretically, our VLANs being created. And so as a result, VLAN 1, web servers, let's say, VLAN 2, databases, workstations, and/or file servers. Everything in the VLAN 1 box, the 2 web servers, well, they're able to interact with each other. They're in the same VLAN. They're members of the same group. Whereas the databases over here in VLAN 2 can see each other and interact with each other, but we're not able to send and receive information to and from members of VLAN 2, to and from members of VLAN 1, unless we're either a member of the VLAN or we have an ability to be in a VLAN that is open to all, a community VLAN, let's say, as opposed to an isolated or closed off VLAN. We're not getting into the distinction here of secondary VLANs, or what we call private VLANs that are nested inside main VLANs to differentiate whether or not they're open to everybody or perhaps open only to a select group. We just keep the VLAN ID simple. You got to be a member of the VLAN. You got to be in the box to see other resources in the box. That's the easiest way to think about it. So as a result, we see that all these VLANs can indeed exist on one simple physical or virtual switch. Doesn't have to be a complicated switch to be able to enable VLANs, just has to have the ability to be able to have them programmed in and somebody who understands how to set them up. But they could all exist in one switch, or we could say theoretically, first 2 VLANs might be in their own switch. There could be another switch down here that would represent the other 2, and whether they're connected or not really wouldn't matter as long as the 2 VLANs that are on the top switch, hypothetically, are connected to each other. In theory, they could send or receive information between each other if we allowed them to, right? So we just want to make sure we understand the logic of VLANs, where they come from, and why potentially they offer us this capability to isolate information management, traffic, and access to resources. Now, does that mean that somebody from outside that VLAN, let's say hypothetically an external user, we saw VLAN 1 was web servers, right? Let's say somebody is outside on the external network on the WAN, totally removed from our network, and wants to access one of those web servers. Would they be able to get in and see the web server from outside? You have to think about that, right? Mm-hmm. I'm going to turn to my esteemed colleague here who's pondering. He's also tailgating off camera, but we're not going to show you that. But come back to us for just a moment if you could, right? Think about this. Would we be able to bring in somebody, just like as usual, let's say maybe it's Parker sitting out there, right? He wants to access that web server. All right. What would we have to do to allow him to do that if the web servers are in the VLAN? I'm going to put the VLAN up just while we're talking. Just give me a second.
Okay. So what we're saying is from a WAN interface to the LAN interface, we put the web servers in a VLAN. So that's going to be LAN side. See, VLAN, I'm thinking, is a LAN-based technology.
Well, but you hit on something that's interesting, right? So, and I have the note on there, but I don't want to show the note before we talked about it, right?
Yeah.
So instead of just saying all the VLANs are internal, what if some of these VLANs were actually public-facing? Meaning, what if we allowed machines in this VLAN to be accessible to the WAN, to the outside world? We're grouping them together because we want them to be isolated from other things. But could they be public-facing?
You know, I'm thinking VLAN hopping attacks, where maybe we don't want to do that. But I'm also thinking, because the VLAN's usually a switching technology, that maybe through remote access technologies, maybe.
Well, so let's think about it this way. Right? Let's remove this and let's look at my note here for just a second. So let me just bring this up here. All right. But let's say, hypothetically, according more or less to my scenario, right?
Sure.
That if all our critical assets were in the same LAN without any segmentation, we just put them all back together without the VLANs, you get into one LAN, you get to everything, right? So we know we need segmentation, right? The question is, can we segment in such a way that instead of just everything's internal but isolated from each other internally, no external, could we segment to allow some internal but also some external within those isolation environments? That's really what we're asking. Okay. So let's say databases, right, which we did have a VLAN for, right, have some sort of solution that must be, right, available, but needs to be separated from the public-facing web servers. Because traditionally in a web stack, you have the web servers and you have the databases where the transactions are stored. We want to heavily defend, to Wes's point, the databases. We want them to be internal, as he was suggesting. But as I'm suggesting, right, the web servers are usually going to have to be available publicly. In other words, in theory, they have to be available from outside of the LAN, right, to use Wes's terminology. So if we were figuring that out, right, and trying to figure out, could we isolate and protect the web servers from the database in such a way that if the attackers got into the web server, they didn't immediately have access to the database servers? The answer is yes, VLANs can help us to do that, even though some of the infrastructure in the VLAN may be accessible from outside, right? Because we're bringing back in this idea of what IP addresses are now going to be assigned and potentially what subnet masks may be used. So we're combining physical and logical isolation as we answer this question. Because the idea now would be that, and Wes hit it right on the head. He was thinking it through the right way to think about this. Well, this is typically inside because it's connected to our switch. Absolutely correct. Couldn't agree more. But that doesn't mean that there may not be a way for this machine to have an external outlet. Remember, the VLAN is an isolation concept that's logical, has nothing to do with physical isolation. We could multi-home this machine, and we could have a separate network card that goes out to the outside world and may even be attached to a separate switch.
Or just add a gateway router. See, I didn't even think about the fact just add the gateway router, and then you've got
remote
routers.
access. You kind of hit on it. You just didn't necessarily call it out, but you're toying with the idea of remote access capabilities there, and a remote access server or a gateway server, something like that, would allow us to have those same capabilities. So what I'm pointing out to you is it's not as obvious on the surface until you start really thinking about, how would I apply this in my world or in the real world, hypothetically, in a scenario? What would I do? If somebody gave me this diagram, how would I create a secure environment that would allow web servers and database servers to be protected, and really harp on the idea of protecting the databases, but knowing the web servers has to be available to the outside world, to the WAN? How can I architect that, right? What would I do? Well, there's a solution. Clearly, we're just missing some of the components, as Wes suggested. There's no router here. There's no gateway of any kind that would let us get out. There's no firewall. We haven't multi-homed the machines. There's a lot of things we would do. I hinted at some of them, kind of give you some of the ideas in my introductory remarks and talked about physical and logical isolation. But I didn't put them all on the diagram on purpose to get you to think about it, right? Because you got to apply the knowledge to be able to answer the questions on the exam. But Wes was in the right place, doing the right things, just like you should be, thinking it through out loud, trying to getting those ideas centered and coordinated and vetted so we can put them to work, and wound up in the right place. Okay, yeah, I'm going to need this, right? I'm going to be worried about protecting the databases. I need some sort of gateway to allow me to be able to get out, and I need some sort of way to physically differentiate that with some sort of additional network interface and probably some sort of different IP address that's publicly available. Or if we want to NAT that device, as we suggested, put the NAT out there in front of those machines and connect the machines to the NAT and allow the NAT to act as a screening device that hides the internal machines, right? right? There's a lot of ways to do that. Then we put the burden on the NAT device as opposed to the burden on the web server directly inside the VLAN. There's a lot of ways to go with that. But you want to keep that in mind and think about that. All right, so when we think about VLANs, we're thinking about virtually isolating using switch-based identifiers, the ability to be able to isolate in like a group these machines and allow access to members in the group, but then tightly control who and what may come in if they're not a member of the VLAN. What about network data flow, and why is network data flow so important? Well, network data flow, as I suggested to you, is really the idea of understanding what kind of data we're dealing with, where it's coming from, where it's going to, and what conditions should be applied to it, countermeasures, controls, protections, policies, to ensure that it is coming from A, going through B, C, and D, getting to E, but doing so according to our expectations and with the appropriate level of protection. So when we think about data flow, we think about network data flow, I find it's helpful to actually create a visual, right? To kind of map out when I talk to customers and talk to students what this looks like. I think of creating right down here a data flow diagram. And so let me show you what I'm thinking of with one of these. Hypothetically, it would look something like this. We have a user sitting over here, and we have some sort of an edge device, maybe several of them, depending on what we're talking about. I put things like a firewall or a content distribution network in there as examples. And behind those edge devices, you'll notice I've got some analytics servers, some databases, but I've also got a bunch of other stuff. I have API management. I have some sort of app server capability. I have integration servers that may be bringing in some of the data from this flow and making it available, given the direction of the arrows here, to databases and analytics servers to feed and send information in for visualization and reporting purposes. This could be a SEM solution, integrating and pulling in log files from different machines and then storing them in a database and applying analytics capabilities to them, for instance, hypothetically. We may have data caches, files, and authentication repositories sitting here being served up to do authentication and a variety of things into and out of the application servers as we go. Notice I didn't put in here, this is a Microsoft solution. I didn't put specific vendor information. This is very generic because we're really not worried about the vendor at this point. We're worried about the logic of the boxes and high-level representation of ideas. So we can begin to see, as a security professional, where the potential landmines may be, where are the sinkholes we have to worry about, and potentially what can go wrong, and what do we want to think about having to bolster and defend more heavily than others, right? I obviously have to think about and worry about the user here, and things like security awareness training and making sure they're aware of policies and making sure we apply verification and validation capabilities to this user when they authenticate, and a variety of things. Multi-factor authentication to prevent spoofing and potentially masquerading attacks. There's a lot of things I think about that would go on there. On the edge server area here, again, depending on what I'm thinking about, I'd be worried about whether or not I'm going to be setting up a DMZ using firewalls. What kind of masking and potential filtering am I going to apply to my CDN, my content distribution capabilities? Are they going to be natted, right? Am I going to be hiding them behind a screening device? Am I going to put them into a DMZ or simply make them available directly from behind the firewall without worrying about necessarily creating a full-blown DMZ to do so? What kind of APIs am I using? Are they open source? Are they proprietary? Do I have to worry about checking the code in the API base in order to understand whether we have potentially embedded credentials and paths and things like that that may be problematic? You'd want to be thinking about the OWASP top 10 web application vulnerability concerns that we've touched on, some of them anyway that we've identified in some other areas. We'll talk more about them coming up in topic 9 in particular, is talk about system and software development life cycles. But I'd want to worry over here about vetting my code and understanding what's in those APIs. What kind of patch management and vulnerability management am I applying to my app servers? What kind of, for that matter, firmware management and vendor management am I applying to all my infrastructure, firewalls inclusive? What kind of data normalization am I using here for my data caches? What kind of storage encryption am I applying, if indeed I am at all? Whole disk encryption, what we call FDE, full disk encryption. In my storage stack, am I doing block level encryption, which I can do in certain storage instances? Am I using only file encryption? Perhaps in my databases up here, I'm not encrypting all the data. I'm only encrypting certain tables or certain select elements. So there's a lot of things I'd be starting to think about as I look at a diagram like this. Now, that's me. That may not be you, and that's fine. But the idea with a data flow diagram is it lets us visualize high-level elements that we can begin to think about differently than if all we do is say a bunch of words. Because I could easily take this down and say, yeah, I got to figure out a way to be able to allow users to send and receive content from an edge server using our API and make sure that we can visualize that data after it hits the data store in the database. That's going to be very different in my mind than the picture I'm showing you. The things I just said are represented by the picture, right? High level, right? 2 sentences, but the granularity, the level of detail, even though it's very high here, is more developed here than it is in my words, at least for the average person, right? If you've done this long enough, you could hear somebody describe that, and you kind of build this mental image, this flow picture in your mind anyway, so you're probably looking at those words differently. But not everybody does that. So it's very important to have data flow diagrams. Keep that in mind. So often making sense of these flows will be the goal of creating a data flow diagram. Now, what are some of the protocols that we may use or the elements that we may use? I mentioned NetFlow. There's also something called SFlow. NetFlow is a proprietary solution, comes to us from Cisco. SFlow is the open source version of NetFlow. And they are both protocols that collect network traffic for data analysis ultimately. They both essentially provide very similar capabilities. NetFlow has become, really, even though it is a Cisco-aligned solution, really become a standard. Many people are using or deploying NetFlow. For instance, VMware tightly integrates NetFlow into their networking stack, so you can use NetFlow capabilities. Many vendors do. You could certainly use SFlow as well, but they do differ slightly, and so you do want to understand the logic, aside from just one being proprietary, one being open source. So NetFlow itself does take these packets from a transmission and aggregates them into what we call a flow, a traditional flow. The flow is exported for processing and then is able to be analyzed using a NetFlow server traditionally, or a NetFlow solution. Another system will receive that flow data and performs the analysis, whatever that may be, making determinations based on things like source and destination address, source and destination port protocols in use, etc. So all the standard stuff we would think of. Whereas SFlow, open source version of NetFlow, does not create what they call a true flow, but rather, because it does not aggregate, let me just highlight, it does not aggregate the packets up into a flow the way NetFlow does, meaning it doesn't gather them all up and create this stream of data that is flowing into the NetFlow server or the endpoint you identify where the aggregation for NetFlow will take place. SFlow doesn't work that way. It performs a random sampling, seemingly randomly, but it samples at a predetermined interval, the packets that are going by. So, maybe 1 in 100, 1 in 5, whatever it may be set to. And as a result, creates what we call an approximation of the network traffic flow. It doesn't create an actual bitstream flow that shows all the data and sends that to the server for analysis. Instead, we sample and we get a rough approximation through an averaging of the data across the flow. So it works slightly differently, and it is important to be aware of that. We send those sample packets into the server and store them, and we analyze those. But we're essentially rolling up and filling in the gaps when we do that. We're not getting a true representation of flow. So it is a little bit different. One may be better than the other, depending on what you want to do. NetFlow is typically going to be used where we see managed switches and we want to be able to capture accurately the data going through them, not only to do analysis, but also understand things potentially, for instance, like if we see building DOS or DDoS traffic coming in, we want to see what those inbound IPs are and the usage patterns. We want NetFlow as opposed to SFlow because it's going to give us better representation of the actual data and the attack vectors that are being used. SFlow will sample, but we're going to miss a lot of that richness along the way. So just want to make sure we're aware of that. Okay. It is so hard to get good help to actually stick around these days. Look at what he's doing. He's in there hanging out and tailgating. I wasn't kidding around. All right, that's it for us here on this episode of IT Pro TV. Join us again. We're coming back with more. Don't go anywhere. And Wes, I promise, is going to be back standing where he belongs. I'm going to go get him right now. We'll see.
Thank you for watching IT Pro TV.